The Nearshore Dewatering for Cost-Effective Underwater Munitions Removal was an ESTCP-sponsored demonstration project, performed by Jacobs' Claudio Fassardi as principal investigator, Heather Rechtenwald as project manager, and Brett Dorr as Jacobs' NAVFAC liaison. Co-performers included NAVFAC and USA Environmental Inc. Past military training and testing activities have resulted in large quantities of underwater munitions present in littoral areas of the United States. Within the formerly used defense sites program alone, the U.S. Army Corps of Engineers has identified more than 400 sites totaling more than 10 million acres, potentially containing munitions in underwater environments. Within the littoral zone, the nearshore represents one of the most complex and logistically challenging environments, where the removal of munitions with divers or remotely operated vehicles and marine equipment is inherently difficult, labor-intensive, unsafe, and costly. Technologies to temporarily dewater impacted nearshore areas to allow for faster, safer, and more economical munitions removal with land-based methods would be a breakthrough in the long-standing problem of addressing explosive hazards in the surf zone. In 2018, Jacobs and USA Environmental Inc. performed a non-time-critical removal action to reduce the explosive hazard associated with nearshore munitions in a small, wave-protected cove at the former Vieques Naval Training Range in Puerto Rico. Unique to this action was the use of a temporary water-filled cofferdam to dewater the impacted area and provide access for land-based equipment and personnel. This action showed that this technology could be used to temporarily dewater nearshore areas to allow for faster, safer, and more economical munitions removal with land-based methods, and led Jacobs to propose a prototype-scale demonstration in a range of commonly encountered nearshore conditions. The objectives of the demonstration were: first, assess the feasibility and develop guidelines and procedures for using temporary, portable cofferdams constructed with water-filled geotubes to dewater nearshore areas, to perform munitions removal faster, safer, and more economically with conventional land-based methods. Second, provide a technology to make the nearshore a safer environment for recreational users and military operations. The site selected for the demonstration was the former Vieques Naval Training Range, or former VNTR, in Vieques, Puerto Rico. Specifically, at the east end of Beach 2 in Bahia Salina del Sur, on the south coast of Vieques. The geotube, manufactured by Aquadam Incorporated, was selected to construct the cofferdam for the demonstration. Aquadams were selected based on its inherited stability derived from its construction, and because it was the most applicable technology available on the market requiring minimal adaptation for the demonstration. Aquadams consist of two basic parts: an external sleeve made of a heavy-duty, permeable woven polypropylene geotextile with a vertical internal stability baffle, and an impermeable polyethylene inner tube. The cofferdam selected for the demonstration was approximately 600 foot long. To facilitate transportation, handling, and construction, the cofferdam consisted of 5 individual tubes joined to each other with connection collars. Several layouts were developed. The final layout consisted of a starter tube deployed in a nominal 5-foot water depth to provide a stable staging platform to begin construction of the cofferdam. It was a 12-foot high, 25-foot wide, and 100-foot long tube featuring 50-foot long connection collars to join, at each end, 12-foot high, 25-foot wide, and 150-foot long wing tubes. The wing tubes featured 50-foot long connection collars to join, at each end, 6-foot high, 13-foot wide, and 100-foot long beach tubes. The cofferdam was constructed in a U-shaped fashion to enclose and dewater an approximately half-acre area. In addition, 2 backup tubes were deployed to provide structural support to the starter and wing tubes in waves. Construction was performed between March 5th to 13th, 2024. On day 1, the backup east tube was launched and deployed. On day 2, the backup west tube was deployed. And by the end of the day, both backup tubes have been deployed. On day 3, the wind was 10 miles per hour, and waves were 1 to 2 foot high, both from the south. Due to these conditions, the construction was postponed. On day 4, the starter tube was deployed, slowing unrolling it by filling, using retaining ropes and jet skis. Because the backup tubes had moved, they did not provide any support and were later retrieved. On day 5, the wing east and west tubes were joined to the starter tube, but not deployed. Once the tubes were joined, the tubes were moored to the beach and offshore anchors. On day 6, the wing east tube was unrolled and filled, assisted with jet skis and controlling the unrolling with retaining ropes. Once the wing east tube was deployed, the beach east tube was joined and deployed. By the end of day, the east end of the cofferdam was constructed and connected to shore. On day 7, the beach west tube was deployed, following the same methodology used for the beach east tube. On day 8, taking advantage of the calm water in the partially enclosed 0.74-acre area, munition divers performed a survey and located 52 anomalies in 4 hours. Unexpectedly, the beach west tube failed, so it was replaced with spare tubes. Dewatering commenced towards the end of the day, but had to be terminated due to seepage at the wing and beach east tubes connection collar. On day 9, the seepage pathway was repaired, and dewatering commenced. Using 4 4-inch pumps and 3 3-inch pumps, about 67% of the enclosed water volume was removed, reducing the enclosed water area from 0.74 to 0.44 acre in 6 hours. Towards end of the day, seepage at the repaired area occurred again, and another seepage occurred at the starter and the wing west tube connection collar. The pumps could not keep up with the seepage. The dewatering was canceled, and the cofferdam construction was considered completed due to the inability to repair the seepage pathways. For 7 days, from March 14th to March 20th, the stability and structural integrity of the cofferdam was monitored by daily visual inspections. On day 2, the beach east tube deflated completely. The other tubes maintained their shape. Between days 3 and 5, the cofferdam was slightly deflated and oscillated in 0.8 to 1 foot waves. On day 6, the cofferdam was significantly deflated and oscillating in 1 to 1.3 foot waves. On day 7, the wing east and west and starter tubes were deflated, so the monitoring was considered complete, and the crew proceeded to remove the cofferdam on the following days. During the cofferdam monitoring, on March 14th, 16th, and 18th, munition divers performed intrusive investigation to identify the previously located 52 anomalies and remove items. Of the 52 anomalies, 41 items were removed, 36 of which were cultural debris, and 5 were munition debris. The remaining 11 anomalies were buried deeper than 12 inches, or were obstructed and were left in place. The tubes were retrieved in 3 days, between March 21st to March 23rd. Achievements: identified the key benefits and flaws of the cofferdam components and layout, identified critical equipment needs and construction crew skills, developed tube deployment methodology and construction sequence, constructed the cofferdam in 6 days, plus 2 days of repairs due to cofferdam seepages and leaks, temporarily dewatered the enclosed area, removing 67% of the water volume and reducing the enclosed water area from 0.74 to 0.44 acre in 6 hours, provided a 0.74 acre wave and current-free area for munition removal, located 52 sub-bottom anomalies in 4 hours. In 3 days, removed 41 items, 5 of which were munition debris. Although dewatering was halted, monitoring of cofferdam integrity and stability followed for 7 days. After monitoring, the cofferdam was removed in 3 days. Critical findings: a wave height limit for construction of about 1 foot was identified. Once constructed, The cofferdam was stable in 1 to 1.5 foot waves. The inner tube material seems too thin as small leaking holes developed, requiring the intermittent filling of most tubes to compensate for leaks. The standard filling hoses were few and small. Additional, stiffer and larger diameter filling hoses, as those used to retrofit the tubes, are needed for fast filling to minimize tube drifting in waves and improve handling during tube deployment. Joining tubes with connection collars was imperfect, leading to seepage and the inability to completely dewater the enclosed area. Wave-induced undertow currents drifted the tubes seaward during deployment, which required beachside and offshore moorings to keep the tubes from drifting further and in position. Strong perimetral straps are needed to moor the tubes. It was difficult to determine the tube fill level. Other than estimating, a method based on a pressure sensor, for example, is needed. It was difficult to empty closed-end tubes, like the backup tubes. Specialty ports and hoses to empty these tubes are needed. While drawbacks to the cofferdam configuration were identified, the demonstration successfully revealed the ability to eliminate waves and currents, making munitions surveys and removal in the nearshore possible and practical. The demonstration evidenced the potential for a cofferdam as a logistically practical, safer, economical, mobile, and functional breakwater to provide a wave and current-free area for munitions removal in the nearshore. If full dewatering is needed, a smaller cofferdam composed of a single tube could be used to overcome the functional challenges associated with connection collars. Advantages over alternatives. The cofferdam is a seminal innovation in terms of safety and cost. It overcomes the conditions that make effective munitions removal within the nearshore with diver and/or equipment practically impossible. The cofferdam provided a wave and current-free enclosed area. Relative to diver or equipment approaches, dewatering or mitigating waves and currents in the nearshore area allows to finding, locating, and removing more items in less time, which leads to better visibility and positioning. Working in safer conditions by effectively eliminating wave and current action. Jacobs and the co-performers thank the ESTCP for its support to this demonstration and for development of munition response technologies.